Yeah, well, just go ahead and jump in. So this project is motivated by the earlier stuff that I've been doing in a whole bunch of various specific contexts in earlier papers, just including one with Craig Callender. So in those papers, I and we discussed this idea of consilience and its breakdown as a test of a concept's limit or applicability. I was mostly interested in what the scope of our scientific concepts are, when they apply, what happens, what can we say when they fail to apply, and I just wanted to study that. So the earliest one I did was on special relativity, where I tried to study how the concept of temperature, the classical one from phenomenological thermodynamics, how that fails to extend in the sense that in the classical domain where it works, where, pre-relativistic domain, a bunch of various features, including theorizing from Carnot cycles, thinking about temperature as the thing you measure with thermometers, which is the end of a long historical episode that Hasao Chang talks about, theorizing from kinetic theory, theorizing from black body radiation. They all agree classically, but they yield different relativistic temperatures when you try to generalize and find analogs of these different procedures in special relativity. Likewise, I've argued in a more recent paper that the concept of pressure may have a similar flavor to it, in that there is this element of choice, like John Otto would say, convention that shows up when you go to this new domain. And it's interesting to me that the semantic content of a concept changes when you go from one domain to another, that now suddenly a choice appears. And this choice seems to be undetermined per se. Of course, you can then bring in other considerations to choose which one you want to pick. My point is that there is this choice that shows up, and that in itself is an interesting change in the physical content of a concept. Likewise, in general relativity, it talked about temperature as well and how it generalizes there. Beyond special relativity, there are new considerations in light of this thing called the Tolman effect that leads one to find more choices, more sorts of open texture, indeterminacy of the concept of temperature when you try to find analogs of them in general relativity. And then more recently, I also worked on extending the concept of work from the classical context into the quantum domain. And then I have argued that there are at least various roles of classical work. They can't all be retained by a single quantum work concept. Again, there's this element of choice that shows up, or an element of openness. And I think it's still an open question that physicists themselves are debating about how to properly extend the concept of work into quantum thermodynamics. So broadly speaking, the methodology is to map a variety of classical roles you might associate with a single concept. You might take it to be these different ways of understanding the same concept and defining them, and then ask what happens when you go beyond the domain in which these procedures were developed, and ask whether the extensions of these, not extensional and not the sense of extensional, but extending of a concept, whether the extension remains consilient, whether they still agree and pick out a unique concept in the new domain. And generally it doesn't. So because it doesn't, there's some new questions that show up, and I want to sort of try to be more constructive and push my own thoughts forward. I think it's true that such tests is useful and helpful because it helps us discover where old concepts fail to apply in new domains, providing us with this evidence of open texture in practice, the idea that concepts may not be delimited in all possible directions, and there's always a possibility of vagueness, as Weismann himself suggested. But I think studying consilience lets us find ways in which concepts fail to extend, and then that lets us understand our concepts better, right? In some sense, they help us refine our concept, and I'll get back to the idea of refining later on as well. But grant that a full classical concept, temperature, work, pressure, suppose they fail to apply in this strong sense that you can no longer find a unique concept that applies in a new domain. What then, right? How do physicists proceed anyway? And can such concepts still do epistemic work even when they no longer apply simpliciter in the strong sense of applying, in that you have the full physical meaning of the concept that you had in the classical case? So our answer, I try to sketch an idea, which is what we call conceptual anchorage. So when we focus on the case of integrable quantum stat mech, which is this fairly new wave of interest in this theoretical structure, even though it's been around since as early as Heisenberg in some ways, like from 1931, Heisenberg chains. But since then, there have been refinement, development, extension of those theories, right? So the point is that in this kind of context, which I will try to gloss over, the concept of classical thermal equilibrium, the idea of a system being in equilibrium with, say, a heat bath, or a system being internally in equilibrium with itself, with some constant temperature T, it no longer applies simplicator to such object. The concept itself doesn't apply. The systems are do not approach classical thermal equilibrium. So in a sense, it just fails to apply, right? And that's like you may say, well, this is open and shut. It doesn't apply. So what? So I thought it's interesting that despite the fact that it doesn't apply, physicists do not simply abandon a concept. Instead, I think it applies in a way I'll call a conceptual anchorage. In the sense that this concept of equilibrium, despite failing, gives us a reference concept, provides us with some frame of reference in this very abstract, slippery way of talking about it. By supplying conceptual resources for identifying what survives in this new domain as analogies, what fails as disanalogies, and together, what sort of new forms of equilibrium reasoning remain possible, despite the fact that thermal equilibrium itself as a concept fails to apply. Right, so that's the thesis of this paper or this talk. We'll talk about how in integrable and near integrable quantum stat mech, we'll get to that when we get there. The consilience, the lining up of these different roles, different ways of defining thermal equilibrium, it no longer stays lined up. It's not consilient. And because of that failure, you're going to have disanalogies. And some may even be thought of as critical, depending on how you think of critical and disanalogies. They're critical in the sense that you might think this is essential to the concept of thermal equilibrium, that it be defined in this certain way. Right? Despite this disanalogies, I would say we will talk about how you can find some more abstract structures, for instance, generalized Gibbs ensembles that preserve this formal, thinner equilibrium structure with disanalogies guiding their applicability. And importantly, we want to say that disanalogies are not just defeaters to the analogical argument, right? That Gibbs ensembles are analogical in some ways to equilibrium. Rather, disanalogies help us pin down specifically delimiting the conditions under which reasoning is possible given this sort of ensemble from the perspective of an equilibrium concept. So the central claim is that classical thermal equilibrium can apply qua contextual anchor, even if it fails to apply simplicator. And you might just say that just means it doesn't apply, and I'm happy to grant that, right? So it's just, I would say there's a sense in which you might think of it as applying, and here's how it will apply. You might think it just doesn't apply, and then that's fine. You can think of this as being a different kind of concept then. So starting to start, we should talk about the consilience. What exactly am I talking about when I talk about the roles of thermal equilibrium? Here are some various things that we can think about based on a variety of theoretical considerations. So firstly, the minus first law or the equilibration principle or the equilibrium principle, depending on who you talk to, it underpins various features of the concept of thermal equilibrium. They're stationary, they don't change in time, they're attractive, things out of the state approaches those states. Uniqueness is supposed to be a unique state that we have in mind, and they're stable. So you're starting with, if you ended up in this state and you left it, you'll under the same constraints, you'll return to the same state. But that's not enough because you only fix the idea of equilibrium. Right? The minus first law picks out equilibrium. We'll talk about the context. Oh, let me just go in. Yeah, so it only defines the unique state of equilibrium. And then there's a hint of what kind of equilibrium we're talking about, because you're talking about finite fixed volume. So there's a kind of constraint you're putting on the system. And then given these constraints, there are further physical meaning. There's a further physical meaning to be cashed out about what sort of equilibrium this is. Right, so this is just the four things I mentioned, right? Stationarity, attraction, uniqueness, and stability. And like I said, the macroscopic external conditions, specific volume. We're not talking about like micro conditions about particular positions of particles, hard billet ball particles. We're talking about like volume. It signals its intended compatibility with classical thermodynamics, in which these variables are the kinds of variables that we'll talk about. And we'll get to the thermodynamic part. But before we get there, I just want to make a side, and it relates to Wayne's talk yesterday. Right? Given classical stat mech already, we have reason to think that this notion of equilibrium, right, unique state of equilibrium, of which you will never leave once you enter it, is a kind of idealization. The minus first law in particular characterizes a state of repose. Once you end up there, there's nothing changes from the macroscopic perspective. But statistical mechanics, right, and even as early as Boltzmann, as Gibbs, reminds us that, and people like Loschmidt and others, Zermelo, right, that on short time scales, we expect fluctuations. Systems come in and out of equilibrium all the time. And recurrences are possible on long time scales, right? Things return to initial states if you wait long enough, right? Extremely long, right? Longer than age of universe for a macroscopic object, but possible given minimal constraints about the state space. And furthermore, exact microscopic stationarity is not necessary for thermal equilibrium. We don't expect when we say that systems are in thermodynamic equilibrium or thermal equilibrium that the particles themselves that we think compose the water or the liquid are literally stationary, literally frozen. That's not the kind of thing that's necessary for thermal equilibrium. Equilibrium is compatible, or to put it in a Heraclidean way, like flux is compatible with stationarity, right? So it's worth emphasizing, even before quantum StatMech, given classical StatMech, the equilibrium is already relative to variables, because you have to choose the kinds of variables that are relevant, for example, volume and so on. The kind of grain, like the details, the time scales, how long you expect the equilibrium to last for, and approximation, because you have to decide what is close enough to equilibrium to call that state an equilibrium state, given the classical StatMech already. And quantum StatMech enriches our understanding of equilibrium by introducing further restrictions or further refinements of the concept of equilibrium. So going back to the point about the physical content of equilibrium, the Minus law specifies equilibrium but not yet thermal equilibrium, because thermal role is pinned down by further effects about the laws, right? Because if the Minus law suffices, then we wouldn't need this other structure. And because it's just like the first pass at the structure, and Aditya's talk yesterday reminds us that there's a lot more details in the structure that you can unpack and like cache out. If you want to talk about what it means for a system to be thermal, like thermodynamic, right? There's a lot more structure you can pin down. By the minimum, there are a few, the three laws of thermo, I guess, 0, 1, 2, 3, 0, 1, 2, depends on whether you care about 3, right? So the zeroth law makes thermal equilibrium transitive, right? The idea that the system's temperature defines equilibrium. And if two systems have the same temperature and they are in contact with each other, they are in equilibrium with each other, right? More precisely, if a system is equilibrium with another and equilibrium with another, then the first system is in equilibrium with the third one, right? And they all have the same temperature. So temperature is the privileged parameter that defines equilibrium given the zeroth law and marks no net heat flow under thermal contact. That is under contact in which they exchange heat. Right? This is important because later on, I'll suggest that under the new kind of theoretical frameworks, you might be able to exchange other things. And then the question is more general. And this is just a very special case of a more broader picture that you get when you get to integrable quantum StatMech or QSM. Importantly, at fixed temperature, the equilibrium state, the unique equilibrium state of the system that we talked about just now, minimizes this thing called the free energy, or Helmholtz free energy, which is defined in terms of the difference between the energy and the product of temperature and entropy. So this is just very basic thermodynamic stuff. So we've talked about the physical content, but for the purposes of this talk, I want to restrict the scope to a more fine-grained version, which is the one that you get after refining with StatMech. We talked about something as statistical thermodynamics of the kind that Diana was talking about earlier, maybe not as detailed from my perspective. What I'll do is not as detailed. So across these different routes for refining thermodynamics via classical StatMech, which I don't want to get into, the Boltzmann-Gibbs debate, the shared explanatory target, I think, is this, that you need to explain why temporal evolution of a system erases the distinctions between initial states. That is, why is the system forgetful? Right? The thought is, if your system is behaving thermodynamically, I can't really know, knowing that system is equilibrium is not enough to tell me where it came from, right? I wouldn't know what the initial state is. Because all I know is that if I waited long enough and now it's in this equilibrium state, I have no idea where it came from. The equilibrium state erases all the distinctions that matter from the initial state perspective, except certain macro properties such as energy and energy and the microscopic details of the initial preparation cease to matter, and the late time statistics and the macro statistics, because we are talking about statistical thermodynamics, depends on a small set of macro variables like temperature, pressure, volume, entropy, and so on. Now, because I say energy, but I'm kind of leaving aside various other macroscopic constraints, right? For example, you may have a particle number constraint, you might have a volume constraint, you have other constraints. But at the minimum, when you talk about thermal equilibrium, energy is the constraint you're talking about. You can generalize it to thermodynamic equilibrium. And we'll come back to this when we talk about the new equilibriums that we find in QSM. So all that's so far so good. We have a whole list of properties we found associated with classical thermal equilibrium. Can we extend it to quantum stat mech? And I think it's a fairly remarkable thing that if you brought some assumptions, you can find domains in quantum stat mech that recovers all the rows that you wanted from thermal equilibrium. You can find thermal equilibrium in quantum stat mech, as long as you made some assumptions. So in the so-called non-integrable case, I'll explain it just a bit. So in this particular domain of quantum stat mech, you can recover thermodynamics by making some assumptions. For instance, by focusing on local observables and reduced mixed state, so subsystem state that's small relative to the giant state of the system. And from there, you can get some pretty nice results. The issue is that I guess for the global state, it is assumed to be in a pure state. And then the entropy of that system never changes. So it's thought that that kind of thing can't be the kind of thing that we study when we study equilibration, because that entropy stays the same under unitary evolution. So instead, we focus on subsystem states. And then once we focus on subsystem states, then the increased entropy is intricately tied to entanglement. Entanglement in some way drives equilibration from this kind of perspective. If you're focusing only in the increase of entropy over time, this is the kind of thing that you want to study when you study entropies increase. Another alternative way, which I won't get into, is to study like the Boltzmann entropy, the quantum Boltzmann entropy, and how that increases. All right. So the point is that in this context, it's great because these kinds of systems that we're going to study are generic. Because they're generic, you say, well, that's a good explanation. Like in some sense, typical systems equilibrate in this way, which I'll go into, right? So on this kind of a domain, you get to find natural quantum analogs of the Gibbs state, which is the statistical definition of a thermal state. You get something like this, which is essentially the same as the classical state. And to get there, you have two steps that you can use for a dynamical story for what's called thermalization, which is the equilibration to a thermal state. So it's similar to the Myers-First law to the kind of state that's characterized by the thermodynamic laws, right? So you can recover that in two steps. First is a dynamical step called dephasing. And this follows from fairly minimal assumptions about the dynamics of a system, focusing only on observables. The O here are observables for a small subsystem of a larger total system, right? For generic many-body systems with many possible eigenstates, energy states, and with this specific consideration about non-degenerate enough energy gaps, depending on how approximate you want it to be, you get the result that the off-diagonal here dies off, and you wait in the infinite time limit, you get this kind of system, which is a diagonal ensemble, so-called diagonal ensemble that's stationary, right? It doesn't change. So and the expected values don't change either. But there could be fluctuations, going back to Wayne's talk, right? So the fluctuations could be large, but there's a sense in which something is stable, the expectation values are stable, right? But the variance may be huge, depending on system size, right? If you go up in like particle numbers, the variance dies down, scaling with 1/√2, and just like Wayne was talking about yesterday. But that's not enough for thermalization, right? Because all I told you is that it approximates something stationary that has some kind of stability, right? And if things approach it, if you wait long enough, things approximately approach that kind of state. But that's not a thermal state yet, because again, the structure of the diagonal, this is the full, I guess in some sense, weights probabilities, or things that can become probabilities associated with each energy state of the system. So it's quite extremely detailed. It's not yet thermal because it doesn't have any forgetfulness at all. To get the kind of forgetfulness, you have to rely on something called ETH, or the eigenstate thermalization hypothesis. Roughly, it says that the relevant diagonal data depends smoothly on energy alone, so that in a narrow enough energy window, you're focusing on the small interval of energy, then the dependence energy makes the observable, the diagonal entries of the density matrix approximately flat, so that it's approximately constant in energy. The energy window is narrow enough so that within the window, each diagonal term is approximately constant. If it's approximately constant, you get to assume something like the principal indifference reasoning, but not because of the reasons associated with principal indifference, just that mathematically you're allowed to just assume that the distribution is roughly flat in the small window, so that you can get the thermal distribution, which just says that the observable depends roughly on depends equally on all possible energies within that narrow window. right? So the point is that dephasing, the thing we talked about earlier, which to do with this and this complicated quantum mechanical dynamics, just removes the memory, the kind of memory of each energy to each other energy state. That's a phase memory. But ETH removes even more of the memory so that the whole thing, whole density matrix only depends on energy in this smooth way so that you can approximate it as a thermal state under certain conditions, recovering the effective forgetfulness of the state. So of course you might say, well, is this really recovering thermodynamics or is this recovering something that's like super like constrained and super narrow? And I would say, yes, it's both, right? Like you need special constraints, but under these constraints, you get back the full thermal state of the system in this way. I mean, that's what we want, right? We want to know when and what conditions we learn that you can do thermodynamics on quantum systems. And the point I should make as well is that that kind of consideration, this consideration doesn't quite depend on system size, right? It depends on it in the implicit way through the possible eigenstates, but principal systems can have many possible eigenstates enough to allow this kind of reasoning without being large enough for thermodynamics in the classical sense. So this is kind of a refinement or adding details to the scope of thermodynamics already. So that's what I mean by it's a refinement of the concept of equilibrium. This depends on energy in the sense that narrow enough depends quite a lot, and the fact that the off-diagonal vanish depends quite a lot on the system size being large enough. Yeah. So the point is for large classes of isolated non-integrable quantum systems, the package is recovered for local observables in this micro thermodynamic equilibrium kind of sense. If you don't know what I'm talking about, that's fine. That's not really important here. The point is that starting with unitary evolution with a single, well, a subsystem of some larger system, you focus only on that system, you look at it evolve. Over time, it first dephase so that the diagonals die off. And then ETH tells us that the diagonals start approximating something like a thermal state of the kind that can be described with the Gibbs state, which is the thermal state of choice under these conditions, right? Under dephasing and eigenstate thermalization. And there's some references if you're interested. So I say all that, right? That's all in terms of the non-integrable case. But I haven't really say what non-integrable is. I'm intentionally leaving it vague because I think the literature is not quite clear about what integrability, non-integrability is per se in this general sense, right? They have very specific conditions, but everyone kind of but different people disagree on which conditions are the right ones. For my purposes here, I'll just say non-integral systems are those that depend only on are only constrained by energy as a conserved quantity. But the integral models, the one we're going to talk about, are those that are constrained by more than energy. They are constrained by additional conserved quantities. This can be written down precisely in the classical StatMech domain, but in the quantum domain it gets trickier because there's some counterexamples and some subtleties. So the point is, we've studied non-integrable quantum domains. What about the integrable one? Right? So in the landmark experiment, Kinoshita, Wenger, and Weiss, in 2006, they prepared one-dimensional Bose gases of 87 rubidium atoms, so a whole bunch of ensembles of them, just let them collide and then wait and see. And the important thing is they focus on the observable momentum, which we already said, observable dependent, right? So we're focusing on momentum. And you want to see the distribution of momentum of these particles after collision over time and how they behave. And you compare them with thermal ones. So if they were to be thermal, so here's where like equilibrium as a thermal equilibrium as a reference state comes in as well. If they were thermal, they would have behaved in this kind of counterfactual way, like on the narrower, peakier distribution, right? But they don't. Instead, they approximate something that's much like distinctively different at this scale from the thermal distribution. So they say the gases that they put into contact with each other do not noticeably equilibrate even after thousands of collisions. Now, of course, there's always a skeptical worry, like, oh, maybe wait like 10,000 times, maybe it might start equilibrating. And that's actually something we'll get to in just a bit, right? So the point here is this is well modeled by integrable model. And it's technically often said to be also a near integrable model because they'll say, well, this maybe is one phase of the longer story of the system in which eventually it might reach a thermal state. We'll get there in just a bit, right? So it's an integrable model. And now I want to know, can I extend concept of thermal equilibrium here, right? Here, on the face of it, it might fail because the gas do not noticeably equilibrate. So it's like, oh, it's not approaching thermal equilibrium. It's not a kind of system that I can look at and I close my eyes, I wait for like 2 hours, I go back and say, oh, that's definitely in thermal equilibrium. That's something we kind of talked about yesterday, right? There's something you can assume for many generic systems like my bottle of water and like other things. But here's a case in which this might not be true. So the concept might not be applicable to the system because it might not be a kind of system that behaves in this way. So just to give a brief introduction, and this is something that's fun as well, but the kind of model they study is usually like a chain of hardcore bosons. Yeah, hardcore bosons because they're bosons, but they don't overlap each other. They interact in a very special way such that they bounce off each other like billiard balls. Right? Of course, that's never going to be exactly true, which is why it's also, when I say here it's well modeled, it's really, it could be an approximation to the underlying model, but it's it's a good description of the system. Right? So there's this kind of hardcore boson algebra, which you don't have to worry about it. But here, the thought is that it's kind of bosonic, but you also have the algebra structure that's kind of, well, what's the fermionic? Yeah, right. So it's kind of weird. And we'll talk about it. We can talk about it Q&A too. Like there's some weird ontological things you can think about here. But the point is that the main observer here is this momentum distribution. And because we are working in the lattice, we talk about quasi momentum. It's not like real continuous momentum. It's like a kind of quasi discrete momentum distribution. You can just define them. Yeah. So the point is that these terms help define a kind of extra conserved quantities in the system beyond the usual one. Obviously, one natural one, if you sum up all the possible particles in those momentum modes, you're going to get the total particle of the system. But there are more conserved quantity. And the way often they do it is to map this kind of bosonic picture to via this super interesting thing called bosonization, right? Or like fermionization, I guess the same thing. There's a duality. A chain of bosons can be mapped to a chain of fermions if you add extra structure onto the fermions. I think it's super cool. By this thing called the Jordan-Wigner transformation. It works in one dimensions, but recent work suggests it can be generalized to arbitrary dimensions, which is work for future work. Yeah, so the point here is that let me just give you this detail so that you know what kind of things we're talking about. Like you have these models, and it tells you the interaction terms between different particles from different sites, the creation operators from different sites. And then you're going to get these kind of conserved quantities depending on the momentum distribution. And the point is that these kinds of, when you check and you see the commutation relation between this and the Hamiltonian, you'll find that these all commute with the Hamiltonian, and they commute with each other as well. And in the classical case, this is one definition of integrability. And so physicists say, in the quantum case too, is a kind of integrable system. It's kind of like an analogical reasoning as well. Future work, whether they relate to each other, right? So the point here is that there are these extra conserved quantities, and they can define them in terms of these kind of things, which are very built out of particle numbers number of particles in the particular momentum that we're interested in. They're typically not ordinary thermodynamic variables. It's important to note, right? So one might say, yeah, this just is like, what's new here? I already have conserved quantities like volume, particle number, and so on. But these are not ordinary ones because they are model specific. It depends extremely on what model you're looking at, right? And there's no like a symmetry consideration that you can use to like, sort of pull them out. Like, you might think like momentum, energy, these are things that are natural. It comes from the consideration of global symmetries of the system. But these ones are highly model specific and can only be graphs when you look at the system itself. We'll come back to some nuances about that. Right? The point is that these do not often have a natural physical meaning beyond the fact that they count certain number of particles in certain momentum modes. There's no like broader macroscopic meaning you might attribute to them. So and this is like a joke that I forgot to take out. But yeah, so the point here is like, what now, right? I want to find thermal equilibrium. I know it's failed, but can we do something close to it? So Rigaud et al. Borrows from our Lord and Savior Lagrange, right? Talked about it yesterday. Like, instead of like talking about God, we can talk about Lagrange here. You appeal to Lagrangian multipliers, right? And we conjecture that following Rigaud, that the standard prescriptions just hold. I'm not gonna tell you why it holds. In fact, in the paper it says, I don't know, like, I have no reason. I'm not giving an argument that it holds. I'm just gonna do it and then show you that you get something out of it, right? You just apply the principle of maximum entropy, maximize the many body entropy, subject to the constraints, importantly, not just by the usual thermodynamic constraints, volume, energy, pressure, and so on, particle number. Instead, you impose all the constraints related to the conserved quantities here. And these are all the local, site-specific, things to do with number of particles at each site relating to each other site and so on. Just do that. Do the Lagrangian optimization techniques, and then you get, at the end, a Gibbs state that looks like this. a Gibbs state. But it's not a Gibbs state because the ordinary Gibbs state has energy here and a temperature associated with it. Sorry, the inverse temperature associated with it. So like BH, beta H, right? And here you have a whole range of them. And the N tells you that there are like as many as the number of sites in your lattice model, as many of them as you please. And then this is just a partition operator. And then from there, you can say, oh, well, I can get prediction results from it. Just take the state, take the trace, get expectation values, and then just look and see the system fits the expectation value. And you can give an argument, simple, relatively straightforward argument that you can obtain this state by optimizing something called the generalized free energy, which instead of you recall the E minus TS, or like U minus TS, you just kind of divide everything across, and then you get this term, this Lagrangian multipliers. Each of them is supposed to relate to a temperature parameter. But now there's no more unique single temperature parameter. You're just going to get a whole range of them and a whole range of conserved quantities minus the entropy. But entropy itself is now suitably generalized as a result. So it looks like, formally speaking, ordinary free energy, but the physical meaning is quite different. And furthermore, you can tell, so now I've found an equilibrium state with some physical meaning. I need to tell you how it equilibrates. You can give some stretchier, generalized equilibrium, generalized ETH story, eigenstate thermalization story, that says that instead of a narrow energy window, you say, well, in a narrow conserved profile window, it's narrow enough, then things are going to be constant along all those, across all those conserved quantities. You get like a generalized thermal state, like a generalized microcanonical ensemble that relates to all these different conserved quantities. You can say again, this is even rarer than the energy one, right? Because it's like highly specific engineered. And I'll say, yeah, true. But maybe in some contexts we do get it. Under those contexts, we can use it for doing things in physics. So to contrast the two, in the non-integral case, the system just has a single energy defined by a Gibbs state with a single temperature. And has an equilibration story to do with ETH that I just said, dephasing plus energy considerations. Here you have a charge profile, a whole bunch of them instead, like in fact, an extensive number of them. So scales with system size. So you can't just ignore them by scaling up the system because as large as the system grows, there will be more and more constraints that grow with them as well. And then instead you get a GGE that again, to remind you, is the exponential of all the conserved quantities with all the Lagrange multipliers associated with them, which you can interpret as a kind of temperature, but the open question what they mean here. And then the generalized ETH, which is again quite a specific assumption of the system. Now, given this kind of setup, the important part to say here is that what we've done here is physicists found that thermal equilibrium fails to apply to the system. We can't find thermal equilibrium system. Then they ask, okay, what can I do next? I still want to do all the good stuff with thermodynamics. Can I still do them? And the question is, oh, can I do them? And let's see how far we go, right? So you'll find a whole bunch of stuff, but for forcing the concept through, you'll find that there are going to be analogies and disanalogies. That is not like surprising. But it's interesting that the analogies are pretty good, pretty nice, and the disanalogies do not prevent you from applying the concept, right? Sorry, do not prevent you from doing this stuff, right? But it prevents you from applying thermal concept because there's no privileged temperature. So the system just isn't a thermal state. It doesn't have the essence of a thermal state, if you want to put it that way. Right? It's stationary, has an attraction story you can tell for equilibration, can be obtained from maximum entropy considerations, variational considerations, and is unique once you fix the full charge profile relevant for the system, which can be can only be determined empirically, like what's the number of conserved quantities relevant for the system. But because of that, you're going to have a lack of privileged temperature because there's a whole bunch of them, and a lot of them may not have anything to do or like have very little to do with the temperature, except under specific conditions. They're not unique relative to energy constraint alone. So if you walked in a room and you looked at a box and you say, well, I know the energy of the system, therefore I know the thermal state. And then you tell them, no, you don't really know the state of the system because you haven't told me the rest of the charges, right? You only told me something approximate, maybe vague, but you have not told me something more precise about it. Or like there's more you can say about the system that is in the physics itself. It's weaker in terms of forgetfulness because it remembers all the conserved quantities, and we'll come to a counterexample in just a bit. It's weaker universally, the same reason. I can't just walk in the room and just use thermodynamics, slap it on the system and say I can do integrable quantum stat mech on it. It depends a lot on the system's context. right? So it loses the black box feature that makes thermodynamics seem apparently universal. Of course, thermodynamics is not universal, right? You should expect thermodynamics to hold everywhere. It holds in some contexts as well, just that those contexts happen to be the ones which we find the most relevant in our macroscopic lives. And there's some questions about the second law. It's going to apply as an interesting kind of constraint where maybe we might have time to talk about it in the Q&A, but instead of ordinarily, there's one variation of the second law that tells you how much work you can extract from the system. Here, it tells you, if you believe the generalizations that I'm going to talk about, that you can extract arbitrary amounts of work related to energy, if you can trade them off in terms of other conserved quantity. Right? So there's kind of relation between conserved quantity you can play on, and the constraint on the system in the second law you get for a system only constrains all the conserved quantities at once. Right? So it's weaker. It doesn't constrain the energy as much as you might think from the classical case. The point is that this generalized Gibbs state, GGE, does not recover the full thermal package. Thermal equilibrium does not apply as a concept to this state. So again, you might say, yeah, it's just maximum entropy, right? We just did what people always have been doing. The method is the same. Nothing has changed. It's true at one level that the method has not changed, right? The GGE does continue a general strategy of constrained equilibrium, but it does not preserve the classical or like the statistical thermodynamic character of the classical constraints. So you can go on if you want to, and you can go on in applying the new balances you find, but only with a full understanding of these disenergies and the kind of scope that they have drawn for you. So there's some response you can give to this kind of my claim that they are different. Maybe you just accept it, right? But I'm just going to say there's some responses you can give. You might say, wow, the constraints are, you might say the constraints just are like maximum entropy, right? You just add constraints, right? So why not? The point is that the constraints are not classical macroscopic variables. They're not of the same flavor. You might say, well, that's just a difference without a distinction without a difference. But I want to say there are differences between the classical constraints, they're typically few, global, and relatively model independent. Whereas the kind of integrable charges we're talking about, they are extensive in numbers. They scale with the larger a system is, the more of these constraints there are. They're local and quasi-local in a model-specific way, depend on where in the system you're looking at, or in other cases, what degrees of freedom you're looking at, in a very model-specific way. And it's tied to a very detailed charge profile in the initial state of the system, rather than a relatively small in comparison thermodynamic state space, depending only on volume, pressure, entropy, and so on, the kind of stuff we learn in school. So the issue, I think, is not that it's adding constraints per se, but the physical character of these constraints, the meaning of these constraints are different. And I think that is a good way to just say this is just not classical, right? I'm not saying they're not good or anything. I'm just saying they're not classical, right? And the good thing is they're not classical because you're finding something new. We're learning something new about the system now, right? The second is that this kind of constraints, there's an extreme case where you just build a GG out of the projection operators of the Hamiltonians themselves, the various projection operators associated with Hamiltonian. So associate each energy state. You can get a constraint too, right? And this is constrained by all the possible energies of every possible part of the system. You can get a thermal state there. If you think that this is thermal, then this is thermal too. But this just is like the maximally informative density matrix, diagonal density matrix associated system, right? And this tells you the exact weights of each eigenstate in each system. That's just a distribution over all the possible energy states. But if this counts as a constraint, if the macroscopic projectors count as constraint, then thermal equilibrium and like mechanical equilibrium really loses its distinction. And thermal equilibrium just loses its classical forgetfulness. And that might be fine, but I want to say that there's an important physical thing we're doing here. And this is just highlighting that if you want to say this is just more thermal equilibrium, this is also thermal equilibrium, right? Unless you have a principal way to cut it off. Because from the perspective of method of maximum entropy, both are just things you can do with the method. So the same method might lead to a different content, the output of the same method maybe have different physical content, right? So thirdly, the generalized free energy is holistic dimension. Right, ordinary thermodynamics, the free energy constraints the extractable work. Well, you just call it work because there was no need to qualify energy work as opposed to some other kind of work. the constraints of the amount of energy what you can take out. But here instead you have a constraint, the free energy constraints, the sum of all the possible works associated with each of the Lagrange multipliers associated with each of the integrable conserved charges, and the amount of one can do with it. And Guranova puts it, the move to generalize free node energy marks a fundamental conceptual difference. And I think it's fair to say it that way. Because energy work is no longer independently privileged in the same way. Finally, I mentioned it just now, but for non-integral systems, the relevant conserved quantities are comparatively easy to find. Of course, you might say, well, it's quite hard to find the particle number, but the particle number is relatively easy to find compared to the individual site-specific particle numbers of a system. I think this gives classical thermodynamics an illusion of universality because, wow, I can walk in the room, I can find the temperature of a system. But again, finding temperature is not easy. Just saying, relatively speaking, it's easier. But for integrable systems, the GG only works after very, very specific, as you saw with my brief detour just now. We look at the Hamiltonian of the system and analyze the different parts of the Hamiltonian and then what kind of terms are conserved. And that's only something you find when you look at the equation of the system, of which charges matter. So the last year all puts it here. In non-integral systems, traditional statement can be used almost as a black box. They point out it's almost. But the same is not true in integrable systems. Okay. And how we make of this, the point just is that GGs are not forgetful in the same way as classical thermal equilibrium, subject to whatever macroscopic constraints you might have. They're just not the same kind of equilibrium. So taking stock on integrability in this tour that I just made, there are these various classical roles, right? And in the integrable case, they are only preserved in a specific way. Only the stationarity is preserved because you get a stationary description if you wait after some time. You get attraction. As a result, you can see as a result extremization by variational considerations, but they're not thermal, and it's not unique relative to energy plus macro constraints alone. And the temperature fragments, or the role of the temperature is now played by a whole bunch of different multipliers. It's not entirely clear always how they relate to the temperature because it's not clear how they all relate or sum up to the energy. In simple cases, you can find a nice relation. In some cases, you can approximate it, all of them. We'll get to it maybe. If the energy scales are close enough, then you can kind of say that, oh, they're really all dependent on some energy scale and give an energy term to it. They're also forgetful because it depends on model-specific conserved charges. But I want to say that the constituents of the classical thermal equilibrium cannot be preserved in a new domain. And the more weight you put to the thermal part, the less likely you think that this will be the case. So we talked about one sense of stability just now, and note that I haven't talked about stability here, which is the last thing, right? So there's a sense of stability we can establish. If a system is in GGE perturbed, and the new Hamiltonian remains integrable, say you change the potential a bit, and then it goes back to the system, then the system re-equilibrates to a GGE relative to some time scale if the Hamiltonian the new Hamiltonian is also integrable. But if the system is close to integrable in this following sense, that the actual Hamiltonian is an integrable one plus some potential term that depends on that is not integrable. So it could be a very small perturbation that's not integrable in the sense that the total Hamiltonian does not have those conserved charges. If you can split out this way, the integrable part has an integrable structure, of course. The potential weakly breaks those charges so that actually really the system is not integrable. And the old charges are not conserved, but are approximately conserved for long enough. So again, the time scales come in explicitly here. And once you see this, then you start seeing a new phenomenon called pre-thermalization. And pre-thermalization tells us, right, that, empirically speaking, if you start off with some initial state, with the Hamiltonian structure, with the weak perturbation, then for some time scales, those perturbations will not matter for the purposes of the dynamics of the system to any observable extent. To that extent, so that determines the time scale, right? To the extent that they don't matter, you get this pre-thermal phase where the system approaches a pre-thermal state described by a GGE. Because remember this part, right? So for some time, this is the only thing that's relevant for the dynamics of the system to approximation. And to that time, that system has a GGE because the integrable structure is at play. But to a longer time, where this noise term starts breaking all the conserved quantities, to the extent that it's broken, you find that the system approaches a thermal state because all the conserved quantities associated with integrable structure is gone, or it starts getting washed out over time. So there's a slow drift towards Gibbs equilibrium. So the initial experiments are done by Grinch et al. 2012, the paper 2012 in Science. But since then, there have been a whole bunch of different ways to try to establish the extent to which this is true, right? And there's a lot of evidence today. People think it happens. The question is, to what extent does it happen? In what systems does it happen? That's still debatable, and people are still trying to find systems for that pre-thermalize in this way, right? Especially, I think this paper is pretty good. I just found it recently, but Malaya, Krishnanan, and Rigo and DeRoque, they have this like whole bunch of different simulations for different types of systems, and they show that there's pre-thermalization that happens in that domain. Interestingly, if I'll talk about reference, right here, they say, yeah, the simple way to see that this happens is to just model a system with just the thermal constraints, and then model a system with this additional constraint, just compare them and see what the difference is, right? Based with other system otherwise being the same. So the same system supports more than one equilibrium-like description in this case, which I think is fascinating. So the same system, you wait for some time, you'll see, oh, it looks like a pre-thermal state, like GGE state. You wait longer, you're going to get a Gibbs state. But this seems to be in a conflict with the minus first law, right? Because the minus first law says you wait, initially in conflict. I'm not saying it's really in conflict, but initially, if I see a puzzle there, the minus first law says that if I left a system subject to certain macroscopic constraints, it uniquely approaches a unique state of equilibrium. But here, which is the unique state of equilibrium? Is it this one or is it this one, right? Which one is the one that you care about? The answer is that, of course, we already said it's idealization, right? When you talk about equilibrium, it never stays in that state forever. Here is just a more extreme, more empirically accessible case of that. You wait long enough, it approaches an equilibrium state. You wait longer, it leaves that equilibrium state and enters another one, right? On this time scale, the unique state you get is this one. On this time scale, the unique state you get this one. Right? So the uniqueness claim itself should be relativized to time scales and observables of interest. So to summarize, thermal equilibrium, I think, falls apart in this similar way. Right. So again, you get stationary attraction uniqueness, and I mentioned stability just now, right? But thermality generically fails. Extensive charge memory remains, and there are many model-specific parameters. And the thermal description only gets recovered at long times if this is only approximate description. So to the extent that this is approximate, these things hold. But these things suggest new worries, or not worries, but like new considerations for understanding the extent to which thermodynamics apply into a system. So I want to say in short that thermal equilibrium as a concept does not apply to integrable or near integral systems simpliciter, right? And to the near integral case, sometimes only in infinite time. Does that mean that integral systems are really not thermodynamics? Suppose that we focus on integral case. Right? Does it mean, it fails to apply, so this is not thermodynamic? Because there's one sense which is true, it simply isn't thermal, right? So that's the sense, the straightforward sense, it's just not thermodynamic in the thermal sense. But the analogy is interesting enough. There's one flat-footed way I ask a question, just is it really thermodynamic, right? Can I really draw a sharp line? And I'll say, yeah, maybe if you draw a strong enough line, it's just not thermodynamic, and that's okay, right? But I can do other things with it. But I want to kind of resist that kind of drawing a sharp line picture a little bit. In part inspired by this paper I found from Stephen Brush from 1966. Interesting at a PSA. So it's just this brush in broad strokes. The difficulty is that one cannot simply say that A is reduced to B. He's talking about reduction of thermodynamics of stemma in this case. Right? He's saying, I'm kind of hesitant to use the word reduction because I don't really know what it means. The difficulty is that one cannot simply say A is reduced to B, because in all the non-trivial historical examples with which he is familiar, A and B both undergo significant changes as a result of the reduction. Right? This is quite different from the way, especially in the 60s, right? Like a philosopher talked about reduction. This is like nice one-way relation. There's the thing that we know to be non-fundamental and like reduced, and then there's a reducing theory that's more fundamental, more general, that's just true, and it's kind of layered picture. And there's like a static picture, given the theories from on high, right? Say Lagrange, maybe the god Lagrange gave you the theories, and then you just like, oh yeah, let me look at the reduction relations between them. But I think in practice, it's something more nuanced than that, right? As he says, the attempt to reduce second law of thermodynamics changed the theory from an absolute theory of the kind that Planck was maybe professing a bit too much, right, to a statistical law. And a significant part of the reducing theory, StatMech itself, came into existence because of this attempt, right? The attempt to understand better thermodynamics and generalize it to mechanical considerations, give rise to statistical mechanics. And then you want to say, in turn, that fed back into, maybe in Diana's talk as well, right? Fed back into mechanics and let us understand mechanics itself in probabilistic terms in some way. And then he says, often the gain from doing this kind of a two-way reduction is a more precise knowledge of the limits of the validity of the original theory. So it's interesting. There's a feedback into the original thing that you're trying to reduce away. You're not trying to discard it. You're trying to understand it better, right? So that it can be used with more confidence within those limits. You're understanding the new limits that you found in this reducing exercise, and indications of what has to be done. So from the reduced theory, I guess the non-fundamental theory, what you want to call it, say thermodynamics, from that perspective, what has to be done to extend it beyond those limits, right? So you find the limits because you're trying to extend to a new case. You find a whole bunch of the I guess possible ways that the thing might fail, and you say, okay, if those don't fail, I have a new theory, right? That's kind of the way of looking at it. So conceptual anchorage, I think, generalizes or maybe specifies it to the context of concept extension, right? So if he's talking about the high level of theory, I suggest that we zoom in, you see the same thing happening at this kind of conceptual level. So recall the thing I tried to argue for, which is thermal equilibrium does not apply simplicated integrable quantum stat mech. I think it's not that controversial, but I just want to make it clear here, right? But we already saw how the new concept of GGEs can be understood in terms of thermal equilibrium as a conceptual anchor, in the sense that there are analogies to an equilibrium, and those lead you to say, oh, GGEs behave just like equilibrium in this way. And concurrently, at the same time, these analogies that tell you that GGs do not behave like equilibrium in this other way. And contrary to some external accounts in which critical disanalogies ruin the analogies, and it depends on how you read Barker's account, right, and Hess's account. Instead of thinking of that kind of picture, we say instead that analogies support projections and disanalogies delimit the scope of those analogies. But both are needed in order to fix the final inferences you can make of the system. So it's not like analogies are being defeated by disanalogies. They're both working together to help you understand the system better. So in this kind of picture, I think I suggest breakdown as an applicable concept does not entail breakdown as a conceptual anchor. So applicability, the failure of applicability does not entail the breakdown of applicability as a conceptual anchor. And just like Brush's quotes, I want to say that anchorage runs in two directions, right? Firstly, there's I guess a diagnostic anchorage. So from the classical thing, the new thing you're trying to find, you can go to the new domain, by forcing the conceptual anchor through, see what happens there, and then you say, oh, given all these new considerations, now I know that the classical thermal state is much more limited than I thought, or like has some assumptions included in that, for instance, that it can't have dependence on I guess it has to have a dependence on energy as a sole privilege or constraint, plus other macroscopic constraints, sparse global constraints, strong forgetfulness in a way. And how strong, that's only something I learned because I have went to the new domain and found new variables from which I can understand how strong the constraint is. Before that, I just say it was forgetful. Now I say, wow, there's a degree of forgetfulness because I can add more detail in, right? And projecting the new concepts is something you can do as well. From the classical domain, I guess this came first. So starting from the classical domain, you force the concept through and you ask, okay, what do I find there? What kind of analogy do I find, right? So the old roles guide discovery of generalized equilibrium, generalized stationarity, mutual equilibrium, heat work, and generalized law. So I'm gonna skip past this because it's just nonsense if I don't explain it. You can find a bunch of laws, right? You just say I've got to force this through, and I think David was saying, yeah, this is just trivial. It's just force from the formalism, which is true, but the physical meaning depends on how to interpret these things, right? So I'm gonna say at least a bit about that. So those kinds of laws require to have at the basis some operational considerations or some operational concepts that follow because you're trying to extend the analogy from equilibrium to equilibrium. You need something like a contact that allows you to exchange the charges beyond just exchanging energy, because if all you're doing is exchanging energy, then you're not going to be touch the charges, or those charges will be disrupted, and then you won't even get to talk about the laws I mentioned. But this is not impossible, I think, to build for some charges. So the question is, how far can we exploit these regularities that we found? Then again, you need a buff that is such that the buff has approximately constant conserved charges in those quantities. Again, not hard to make, but not impossible, I think. likewise for battery that can do work in those kind of charges. So this, you may, if you are familiar with resource theory, these are kind of related to the kind of resource theoretic picture that Guranova was working in, and I'm just so in the end, the thing you get is going to be very specific. It's going to be interaction relative, depending on kind of system you're going to get. And generic kinds of context are going to break the integrability. So the laws are going to hold only at the scales, a specific kind of scales. But that's something you find out. You go to the lab and you do it. I'm not going to tell you a priori. I know what the scales are, right? The laws hold at some points. To the extent that they hold, they can be useful, even approximately. And then there are going to be generalized considerations for about constraints of free energy. Let's say here that these are not bad things for what I'm doing, right? These are like things that you need to know so that you can then go and do the good stuff, right? If I just told you these laws and say, yeah, these laws are true, you might think, well, what are you really telling me? But I say, well, for those to be true, for them to apply the systems, you need to go and do all these things. These things are the things that you have to do, right? And like these are things that I can't tell you like from an armchair. They specify conditions under which the analogies are licensed, and they work together to support the anchorage. So what's new here is the application of a concept, equilibrium, even though it fails as a complete description. And there's this kind of bidirectional interconceptual relation or intertheoretic, depending on how you see it, rather than a one-way reduction, because the new concept revises the O and the O informs the new. And the disanalogies here delimit the scope of analogies. It's not just about breakdown. And finally, all I want to say before from this is that I'm not saying that this is like, you should always be doing this, right? I'm saying that you should do this and see what happens, and then go and see what you can do with this. Right? So the license is not by some a priori consideration. It's about what kinds of things you can do with the system, what kind of predictions you can make, what explanations can I give, what kind of control you have if you're able to make these things and do things with the system. And it's probably true that most anchors are useless. If you try to force through the concept of Aristotelian substance, maybe you can also do this. You might not find useful laws to work with. I'm not sure. Maybe you can. We try to do like numerology and stuff like that. Right, so what I have done is a story of how to proceed with concept extension after constraints has failed and how to identify good anchors. So in wrapping up, the upshot is that the critical disanalogy in this kind of cases may not terminate a clear inquiry, but rather you can qualify the analogy by fixing the domain and the content of the project. So instead of asking whether analogy really survives, for instance, if you might think that black hole thermodynamics, you can ask whether it really is thermodynamic, and you say, well, there's a whole bunch of this analogy, so it's not thermodynamic. Maybe just ask which analogies survive given the disanalogies. And then the question is, can you ignore them? I think this is still an important question to ask. You can't just say, well, disanalogies are always fine. But you want to ask, do we have good reasons to ignore those disanalogies in the context of consideration? That's more important than whether there are disanalogies at all, because there will always be disanalogies, I think, whenever you do this kind of task. And the reduction thing, I kind of said enough. I'm going to say it's a bidirectional thing. I'm going to try to refine the concept. Reduction may be too coarse-grained a concept for the kind of thing we want to study when we study intertheory relations. So yeah, concepts can apply conceptual anchors, even when they don't apply Statistical. That's the upshot. Right. Thank you.
Okay, thanks, Eugene. Got lots of questions. Wayne, Helen, Aditya, Julius.
Yeah, from book.
Thank you for this. This is, as you know, I find this very interesting because this is the second time I've seen this talk. Yeah. Give me if I've asked you this before, because if I have, I've forgotten the answer. What is the Q doing? What work is the Q doing in QSM? And the reason is that most of what you say goes through perfectly well in classical statistical mechanics. If I have an integral system, if I've got some extensive variables other than the energy, then I can't possibly have a unique equilibrium that's a function only of the energy, and the appropriate thing to do is a generalized Gibbs state. And if I'm recalling correctly, Gibbs said that. Is it now? Just real quickly, I think the answer is those things are going to be hard to come by in classical mechanics, but quantum mechanics gives us resources for defining these things in something like realistic, extensive conserved variables in something like realistic systems. Is that right?
Yeah, no, thanks. That's a good question. You've definitely asked that before. But we talked about it. I think it was good. I think we were talking about it, and I was saying that these quantities conserved here are not of the same flavor, and it's I think the kind of you might be able to you can still do the macro constraints, but the question, can you do more, right? So like if I only have pressure, you can still test the pressure of a big system, right? It's just how much is it really inform you of the dynamics of the system, which is why you can get you can go back to the right. So yeah. So the dotted line is the kind of thing you would get if you only considered the energy constraint. And I think the similar thing can be done if you say, oh, if I only consider the volume or the pressure and other macroscopic constraints of the system. So you can still do it because it's like a counterfactual thing. It's like if the system were only constrained by those things, there would be a prediction. It's just that the prediction is not quite as accurate as if I added new considerations in. And those considerations don't come from macro thermodynamics. Yeah.
How does the fact that we're dealing with quantum rather than classical statistical mechanics help? Because like virtually everything you said goes through if in fact we've got a classical system with extensive conserved quantities other than the energy.
Yeah, no, I think you're right that the general method will be the same, but the systems you find, well, these are specific quantum systems, right? The spin systems, spin chains that I guess they can have classical spin chains too, but like the quantum spin chains are the one they're interested in, and then the models tell you, well, what kind of conserved quantities do I need to take into account? That's something you only get when you look at the spin chain and the quantum Hamiltonian of the system, and then you identify the conserved quantities. I think what's interesting too is like the conserved quantities are local. And I think again that might not be. I mean, you could probably do it in classical too if you knew the subparts of the system. You can probably have constraints of those systems because the point to make too is that there are classical integrable systems too, right? So I think it's true that the integrable reasoning, integrable stuff I mentioned here would have an analog in classical mechanics. The interesting thing is that people have not studied those things until after the quantum stuff was studied, and then they went back and they're like, oh, look, we can of course find a generalized Gibbs state in classical StatMech too, but no one really studied that because there a lot of discussions centered on the KM theorems, like the theorems to do with integrability and the periodicity of the orbits, but they didn't really study how we could still model it statistically in some sense until the quantum case suggested that. So I think it's interesting that the quantum case was the impetus for refining or improving understanding of the, leading to, methodologically speaking, a better understanding of the classical case as well. But I agree with you that in principle, the classical case has the same structure of this as well. I'm not saying that it only happens in quantum. Yeah.
To give it first to Yichen.
Yeah, right. Yeah.
Just want to add to Eugene's reply. I think Miguel is right that the Q is doing, I think, like three things. First one is to make the difference clear, and then second is add more realistic models and examples that are in the physics literature to that. And the third one is because, like Eugene mentioned, the conceptual anchorage, the energy and disenergy are bidirectional, so that like studying the Q part can help us understand better like the classical part. And also there's like interest about what exactly the eigenstate thermalization hypothesis is doing the work, so that we can use the classical cases to help us understand the explanatory power of this new like principle that physicists use a lot in the context of quantum physics.
This is the finger. This is the second half of, I think, Wayne's question, which is that I think what's happening here in this case is that energy is playing an important role. And the way Gibbs and Einstein define a thermal equilibrium, they define it in terms of energy as being constant of motion. And the goal is, the aim is to find a distribution that it has energy as a constant of motion and that remains stationary. And then that yields for an equilibrium for Gibbs and Einstein. I think in this case, what's happening is that you show there are multiple constraints that could be equally relevant, and that could lead to a GGE. To go from a GGE to go to thermal equilibrium, you need an additional term, which is the noise. And the noise then helps eliminate other conserved quantities, and then you end up with the energy as being only conserved quantity. So I think what's important in this case is that if we are comparing, a quantum equilibrium state to a classical state, the analogy will only hold when the context in which it was defined is retained, which is the context of energy as being a constant of motion, over which both Gibbs and Einstein define equilibrium. Of course, as also Wayne mentioned, when you add more kinds of quantities, you can have a GGE also in the classical sense.
Yeah.
So if you could say something more about that, that'll be great. Thanks.
Sorry, what do you mean to say more about? Like, I guess I agree with what you said. So I was wondering what the
So the difference essentially is just that what is the constant of motion? The difference is that what is the constant of motion that we care about in terms of equilibrium?
Yeah.
If energy is the constant of motion, so it's a very long finger. So it's an exchange of fingers.
it's growing longer now.
Yeah, the last finger. And so if it's energy, then the analogy is maintained through and through.
Yeah.
And if it's other constants of motion, we can also happen classically.
Hmm.
Then I'm not sure whether the analogy actually breaks in principle. It could be retained in classical sense as well. Thanks.
Oh yeah. Yeah, so to just say a bit so far, yeah, we agree that if you only focus on energy, that's just the non-integrable key, right? That's why I argue that energy goes through. I think I mentioned somewhere here. Yeah, anyway, yeah, I mentioned somewhere here. Like it goes through. So that's fine. And in the non-integrable case, it's true that in classical systems there are integrable classical statistical mechanical systems too, but there are also quantum classical statistical mechanical systems. And it's interesting to see the kind of considerations show up here to do with this kind of systems have this kind of weird constraints that it's not clear how you will get from ordinary thermodynamic reasoning. But that's true also of the classical StatMech case. I'm not saying that, again, I'm not saying that this only happens I'm using it as a case study for understanding concept extension, right? You can extend it in the classical case too, but the fact of the matter is that historically, it happens like last few years, right? But like historically, like this happened first, or like this happened more prominently, especially in recent 20 years or so. And that's why I'm studying it. Yeah. And I think it's, yeah.
Okay, thanks, Eugene, for the talk. Okay, so I have a question that's kind of a cheap question about the conceptual anchorage. So I'm wondering how, like, what you can say about how to predict what the analogies versus disanalogies will be. And I'm worried, like, otherwise it just kind of looks like some stuff gets carried over, some stuff doesn't. And I'm asking this also because I know that varieties of realism also struggle with this of like finding what will get carried through theory change. So I'm seeing it as a kind of similar question that maybe a local realism would be concerned with.
Yeah, good. So let me go to the point. The question is, how do I predict what analogies will come? I think that depends on the concept you're doing, right? And honestly, I don't think there's an a priori way to get it. I think it's cheap in the sense that, yeah, I only get it once I do it. And in fact, I think the more interesting point is that I never know the full set of disanalogies. Right? There might still be disanalogies I haven't studied yet. I think that's the interesting thing, that it's always a work in progress. You kind of have to go and keep working on it and studying whether there are disanalogies or not. Maybe this ties into my broader appetite for this kind of what's it called, like thought fallibilism in science, right? Like our stuff, me and Yichen stuff on idealization, similar flavor too, right? You never know if you're fully de-idealized. You only know at the end of inquiry or something. I mean, even that I don't know, right? So the point is to keep checking to see if you have any other disanalogies to find. Here are the initial sets that we found just by eyeballing the definition and seeing what carries through. There may be other weird things that show up. For instance, once you start, when you start building this, you're gonna get a whole bunch of other stuff that shows up, right? Because I haven't really said what batteries are, what baths are. You have to build those things, or like consider how to build them. Once you do that, you're gonna have other situations. And then I agree with you, which I kind of mentioned at the end that most anchors are probably useless. Right? Like I said, you can force through the concept of substance. You say, what is the Aristotelian substance really? And I want to use that concept. You're gonna use it, and then you can find a whole bunch of disanalogies, or maybe a whole bunch of weird stuff. Then it's like, can I do anything with it? If I do, then why not? Right? It's a fact of the matter that these analogies carry over, right? And then the question is, what can you do with them? I think the point is to just kind of deflate this question about whether something is really something else by appealing this kind of this picture, because once you look at the inter-theory relations, even in classical StatMech, as you're saying, you're gonna find all these kind of weird situations showing up. Often it's a choice rather than something forced upon us that we choose a certain analogy, and that's because we find it useful in certain ways. Yeah.
I want to make sure I didn't forget any other. You still had a hand that's different from the and Euler's has one. It's a hand. Okay. So I'm going to give it to Euler's, then I put myself on the list. And then maybe we have time for Didier again. But since he lost all his fingers already, they've fallen off. Actually, I have another question about these analogies. So just kind of thinking about the notion of conceptual anchorage, which I kind of like. I'm kind of wondering how strongly it is tied to a type of an account of analogy that you're working with. So I'm thinking of Norton's kind of super minimalist account of analogy in terms of material theory of induction, which kind of entirely ignores this analogy and just focuses on the warranting fact that gives you the induction, blah, blah, blah.
Yeah.
And so do you think, but however, it seems that in this case, it's these analogies that actually do a lot of kind of work in anchoring. So yeah, I'm just wondering what are your thoughts on this? Do you think a minimalist account of analogy could support anchorage?
Yeah.
Yeah.
Well, that's good.
So then perhaps it's, perhaps like a criteria of selection of an account of analogy even, I don't know.
Yeah, I would say I haven't started thinking about what kind of counter analogies would I guess I'm curious what kind of analogy would fail for this kind of picture where I don't really think I'm resting on any particular detail of the theory of analogy, but it might, right? Because that'll be interesting to see which ones don't apply. I think I'm using it rather like straightforwardly, like it's just like, oh, there are things that, oh, I guess in the case of yeah, it's similar, right? And similarity is always hard to pin down, right? Where I say like these roles are similar across these cases. Of course, they're not identical because the content is different, but they are similar in relevant ways. And then the question is, can we judge them to be similar in these ways? We can, and then the flip side is that they will come with all these analogies, the ways in which they're not similar. I think that's kind of all I'm thinking about. It might be that if you put in, say, a rich theory of analogies, this might. Yeah. 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 Yeah, I haven't thought through that too, but we talk more about this. It'll be useful. Yeah. Thanks.
Okay, I have a question, and I think then your question will be in a coffee break. I'm sorry, since we're 5 minutes over. And we can't go too much over because we have one talk on Zoom, so we coordinate with the speakers. So my question is about the, you talk about, like, it's a cheap question in Helen's. It's just about the conceptual work you're doing.
Yeah.
So you talk about the diagnostic anchorage in two ways, right? You have this generic way of saying it reveals hidden assumptions, and then you have a more specific way where you talk about delimitation of the domain of applicability.
Right. Yeah.
And I wonder whether what you like, are those two reducible to each other? So is the way in which the conceptual anchor in the new domain acts diagnostically, or like the anchoring in the new is act diagnostically only by delimiting applicability, or is it perhaps that we also learn to, I don't know, we learn something new just about the theory and the conceptual structure within the old domain of applicability? So what exactly do you mean by the revealing hidden assumptions?
That's a good question. Yeah. I do think I think we learn new things about the theory in virtue of what is needed for this part to hold as well, right? Because here is that, oh, in this case, you will need all these charges, right? So that means in this case, you don't need all those charges, right? So that's one way of learning that this is a pretty generic system. In a way, this kind of setup helps. And I guess in the classical case, again, going back to, it will help like projects like, say, Roman Frick's project for arguing for equilibration, because there will always be this kind of KM concert worry that, oh, if your system were weird in this way, it would not equilibrate, right? And here it's like, wow, if it didn't equilibrate, it would look like this, and this will be at least one version of this, and they will be quite weird. Like this kind of systems in real life, you engineer them with like one-dimensional gases in like ultra cold refrigerators, and that's not the kind of systems we expect our room to be in. And this helps you understand the scope and maybe generality even of the kind of systems that we're talking about here. And I think that's so maybe it's two sides of the same. It reveals the hidden assumptions of this, but it also delimits what needs to be happening here. The two sides of the same thing. At least for the case of the charges, I think it's a clear case.
Okay. Yeah. Let me clarify over coffee.
Yeah.
Okay, let's thank Eugene again for a fantastic talk.